Over the course of the last couple of weeks or so, news has filtered out that one of the brightest stars visible in the nighttime sky has dimmed to about half or even less of its original brightness over the course of the last 2 months. This star, seen as the upper right-hand shoulder of the constellation Orion, if you're viewing from outside the celestial sphere, or if you're looking from the surface of the Earth, it's actually the left-hand shoulder. It's the red supergiant known as Alpha Orionis by its astronomical designation, or Betelgeuse by its common name. While this dimming trend has been noted by astronomers both professional and amateur, the amount of the dimming, how much dimmer the star has become, has caught nearly everyone by surprise. With the developing news making its way out into the broader scientific and science-interested community, a question has begun to be asked. Was one of the largest stars in the solar neighborhood about to explode in a cataclysmic release of energy? Soon, Twitter and other social media channels were abuzz about the possibility of one of the rarest and most spectacular events in the cosmos, a supernova, taking place in the near future. But how realistic is this expectation? Are we about to witness a phenomenon not seen up close since the days of Johannes Kepler? In this episode of the Scientific Odyssey, Unscripted, we'll take a look at both the science and the hype to get a better understanding of what's taking place. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Unscripted episode. Betelgeuse. Is he about to blow? So welcome to this unscripted episode of the Scientific Odyssey. This is something we do from time to time when a piece of information or news pops up or just something strikes my fancy, or I sort of want to riff a little bit. So I've got some prepared notes for what we're going to talk about, but understand this isn't going to be an episode that's as polished or necessarily, I guess, as well sourced or researched in some respects as some of the other episodes that we do. So with that having been said, let's go ahead and get into the material. If you were to go outside on a clear winter evening, which is, by the way, at the time of year when this episode is being recorded, and you look towards the southern sky if you're in the northern hemisphere, you'll see a pattern of stars that's been recognized by humans across almost every culture as far back as our knowledge of astronomy goes. The group of stars consists mainly of a rectangle of 4 bright stars that's, as one source I read said, sort of pulled together by a belt or line of 3 stars that runs through the middle of the rectangle. And this grouping of stars, what we would call a constellation or an asterism, is usually represented by some sort of anthropomorphized figure. It was known to the Greeks as Orion the Hunter, of course, and he figured prominently in their mythological stories. To the Arabs, it's known as the Giant, or the Great One. The ancient Egyptians identified the grouping as Sa, who was the father of the gods. In North America, the Navajo people of the desert Southwest call the grouping the First Slender One, a protector of the star people children that follow him in the nighttime sky. North of the Great Lakes, the Ojibwe people call him the Winter Maker, as his appearance in the nighttime sky signals the arrival of the cold winds and snows. While in each case the specific stars and their arrangement or connection vary somewhat, they all have one thing in common: a particularly bright red star that we know as Betelgeuse. The name comes from Arabic and it means either hand or armpit of the giant, and it's known as Alpha Orionis in our modern designation, and that was given to it first in about 1603 by the astronomer Johann Bayer, who was a contemporary of Kepler's. What's odd about Bayer's designation is that usually the alpha naming in a constellation is reserved for the brightest star in that constellation, and Betelgeuse is generally not as bright as the star Rigel in Orion. So what's the explanation for that? Well, it turns out that Betelgeuse is what we call a variable star. That's something we talked about in our, finding our place in the solar system or universe episodes when we talked about the work at the Harvard College Observatory. There was this real huge effort to sort of study stars whose brightness changed. And that's what happens with Betelgeuse. Its brightness changes over time in what astronomers tend to call a semi-regular way. In other words, the star gets brighter and dimmer in a somewhat predictable cycle or set of cycles. The first person to make good observations of this variability was our old friend John Herschel, who was the son of William Herschel, and he observed that on at least 2 occasions, once in 1837 and again in 1849, Betelgeuse was in fact brighter than Rigel. From this, historians of astronomy sort of think that Bayer probably made his observations of the star at a time when the star was at its peak brightness, and so probably would have been brighter than Rigel. The best set of observations comes from the organization Edward Pickering originally founded, what is now known as the American Association of Variable Star Observers. And the range of change is a factor of about 2.5 in brightness from the dimmest that Betelgeuse will be. It'll get about 2.5 times brighter by the time it gets to the brightest it's going to be. So what else do we know about Betelgeuse? And by the way, let me just pause here before I jump into that. One of the most interesting things and one of the biggest sort of topics of discussion in astronomy and sometimes is actually how do you pronounce the word, the name of the star. If you go out and you sort of look online, it seems to be about 4 different pronunciations. I'm going to go with Betelgeuse. Okay. If you have a preference, I hope this doesn't grate on you too much if this isn't your preference, but this is the sort of the way that I learned to say it. A lot of folks know it, and this is probably not the best way to say it, but a lot of folks know the star is Betelgeuse, and not to be confused with that movie that you might have seen back in the 80s. Anyway, so what do we know about Betelgeuse? Well, because it's fairly close, we've been able to measure a parallax shift for the star, which allows us to determine its distance from the Earth. Okay, and that's pretty interesting. We can do that thing where what we do is we sort of look at where the star is compared to stuff that's farther away on one side of the Earth's orbit and then on the other side of the Earth's orbit, and we can kind of look at the shift. And when we do that, we can then sort of figure out how far away the star is going to be. So the Hipparcos satellite measured a parallax shift of about 6.55 milliarc seconds. That's sort of, 6.55 thousandths of an arc second. If you recall, an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree, and a degree is about twice the size of the sun or the moon in the sky. So if you take that number from the Hipparcos satellite, that's 6.55 milliarc seconds, that gives you a distance, when you do the math, of about 520 light years. Now, more recently, this has been revised by measurements made by the Very Large Array Radio Telescope, and they got a slightly smaller parallax shift. And so when you get a smaller parallax shift, that's because that sort of gives you a calculation that makes the object farther away. That the shifting happens less if the object's farther away. So the number that the Very Large Array has gotten is about 640 light years away. While both of these measurements do have some error, and we're going to talk about that a little later on in the episode, it's hoped that the Gaia spacecraft will be able to narrow down some of those uncertainties, maybe by an order of magnitude, and thus give us a really much better estimate. Hence, if you read about the distance of the star, what you're going to see is you're going to see a number that's usually around 600, and a lot of times the writers of articles and such will just sort of couch that in very vague terms. So it's about 600 light years away. So if you go out and you look up at the arm or the armpit of the giant, depending on, how you translate that word, and you do that after listening to tonight's episode, know that you're looking at the star as it was not as it is right now, but as it was 600 or so years ago, because as we've talked about before, that's how long it takes the light to travel from the star to travel across the intervening space to come into your eyeballs. So that's really kind of an interesting thing. You're looking at the star as it was 600 years in the past or so, not as it is now. Another thing that we can actually measure, and this is one of the first stars we were able to do this with, is we can measure the actual apparent size of the star's disk. Now, the best way to sort of think about this is you can actually do this with the sun, right? I mean, you go out and, you shouldn't look at the sun with your eyes, but you get a sense if you sort of look in the area of the sun in the sky, you get a sense that, okay, it's about this big, and it turns out it's about a half a degree. So you can do the same kind of thing if you've got magnification for Betelgeuse. Okay, and so the first astronomers to do that, to actually measure the size of the disk of the star, were Albert Michelson and Francis Peace. And they did that when they took, in 1920, they mounted this big instrument known as an interferometer to Hale's recently completed 100-inch Hooker telescope at Mount Wilson. And they were able to measure an angular diameter of the disk that was about 0.05 arc seconds. Now, that figure's only been improved upon, a little bit in the intervening century, which tells you those guys did a pretty good job, and their instrumentation and their experimental apparatus was pretty great. Combining this with the distance from that parallax measurement, it gives you a size of the star of around 3.6 astronomical units. So what's an astronomical unit? Well, that's the distance from our sun to the Earth. Now we call that an astronomical unit. And that goes all the way, by the way, back to Copernicus, because he didn't actually know how to calculate the real physical distance in some sort of Earth-based measurement unit. So he did all of his work and he said, hey, we're just going to treat the distance from the sun to the Earth as one astronomical unit. And then we can sort of predict how far away, or we can model how far away the other planets are from the sun and get a sort of a scale model of the solar system. So what this means is if you were to take Betelgeuse and you were to drop it in where the sun is in our solar system, that would mean that, it's 3.6 astronomical units. So the star is going to swallow up Mercury, it's going to swallow up Venus, it's going to swallow up the Earth, because the Earth is only at 1. Mars is at 1.52 or so, right? So it's going to swallow up Mars, and it's going to swallow up much of the asteroid belt. So, you drop that star in here and its size, the whole inner solar system would be inside of the star Betelgeuse. Now, things actually get even more interesting than that. As we said, Betelgeuse is a variable star, meaning its brightness changes. However, along with the change in how much light the star gives off, it seems to actually be that the star changes in size as well. In other words, the star oscillates in getting bigger and smaller, meaning that when it swells up to its maximum size, it probably reaches all the way out to Jupiter's orbit, and when it shrinks down, it might be inside of the asteroid belt. And we're going to talk a little bit about why Betelgeuse is doing this later on in our episode today. As noted before, the star is reddish in color. It's something that's been observed since antiquity. Claudius Ptolemaeus, who we were just talking about in our episode on Greek geography, he was also an astronomer, and he designated the color hypokyrros, or ruddy. Okay, that's how that word gets translated out of the Greek. Interestingly, however, if you actually go poke around in the Chinese records, and the Chinese astronomers did the same sorts of things that the astronomers around the Mediterranean and in Persia and all of that. They would go out and they would observe the sky and they'd make notes about what they saw. And as near as we can tell from these earlier Chinese records, and they go about 3 centuries earlier at least than Ptolemy's, they indicate that the star actually had a yellow coloration. So what you have is the star in over 3 centuries changed from being yellower to redder, if in fact that's true. Okay, and that, by the way, gives us some insight into the evolution of the star over time. So we'll come back and talk about that as well. The Italian astronomer Angelo Secchi, who was so instrumental in the early process of stellar classification, put Betelgeuse in his Class 3 designation as a prototype for the grouping of orange to red stars. In our modern stellar classification scheme, it's known as an M1 or M2 star, but one of the things that's really interesting is it doesn't look like a lot of M1, M2 stars that we look at. And the reason for that is when you take the spectra of the star, what you notice is the presence of strong emission lines in its spectrum. Usually when you look at a star like our sun, what you see a bunch of absorption lines in the spectrum. In Betelgeuse and other stars like it, you see strong lines of emission of light. And so what that does is, because of some of the things that we know, that tells us that Betelgeuse is not a typical what you would call dwarf star, but rather is a supergiant star. which is, of course, something you can tell also by its just enormous size. Now, the final thing to discuss here before we move on and start working on some other things, as we're just sort of looking at data about the star, and that is the star's mass. Now, the difficulty with this is the star, Betelgeuse, has no companion, at least as far as we think, right? There's been a few observations that suggest that maybe there's one, but those really haven't been confirmed. So right now, the working model is the star has no companions. And since it doesn't have any companions, we can't use Kepler's law to determine a value for the star's mass directly. Instead, what we have to do is we have to use the mass-luminosity relationship that was determined back at the beginning of the 20th century. Now, luminosity is a measurement of the total amount of light given off by a star. Due to its relatively low temperature, Betelgeuse is only about 3,600 Kelvin, so the surface temperature of the star is actually lower than that of our own sun. Betelgeuse gives off only a fraction of its light in the visible part of the spectrum, with the majority of its energy actually being emitted in the infrared portion of the electromagnetic spectrum. Okay, so in fact, if we could see the infrared part of the spectrum, if we had like the eyes of some birds of prey or something, Betelgeuse would be by far the brightest star in the sky. The total amount of energy given off by the star ranges between about 90,000 and 150,000 times the amount of light given off by our sun, which, if you do the calculation using the mass-luminosity relationship, that puts Betelgeuse's mass somewhere around about 11.5 times the mass of our own sun. So, with that information all out there, the question is, again, what's going on with Betelgeuse? Well, over the course of the last 2 or so months, the star has gotten dimmer by more than a factor of 3, with the AAVSO, that Variable Star Observing Organization, reporting that the star is dimmer than it's ever been in the 100 or so years they've been making measurements of its brightness. This nearly unprecedented drop in brightness has led to a good bit of media hype, with major news outlets such as CNN devoting space to both the observations and the speculation about what the trend means. Far and away, of course, the most sensational explanation for the dimming is that the star is about to explode in something called a supernova. For reasons that we'll discuss here in just a bit, this explanation is in fact plausible, but it's pretty unlikely. What's a lot more probable, and what's probably really a lot more likely as an explanation, is that a combination of physical factors that lead to 3 different variability cycles are combining to cause the light emitted by the star to be at a short-term minimum. So let's see if we can try to understand a little bit of what's going on here. Before we do that, though, I want to take just a minute and I want to talk about something that we've sort of hinted at up in this sort of, which we were talking about, the physical characteristics of Betelgeuse coming into this section. And that is, we have a real difficulty nailing down some of those physical characteristics. I mean, we don't know exactly how far away it is. We actually don't know how big it is exactly. And, we don't know its mass exactly. We don't have exact measurements of those things. And I want to talk a little bit about that. And I want to talk about sort of how that works in science. So in a sense, this little section here is my little sort of thing that I try to do in each episode, where I talk a little bit about some of the philosophy of science kinds of things. One of the things, if you read Alder's book, The Measure of All Things, it's a book we've talked about here on the podcast in the past episodes, is Alder makes the claim, and I think there's some validity to it, though, probably there's some people who are going to push back pretty hard on this, and that is, you really can't call something science until you can talk about things like error and uncertainty, and you can figure out how to sort of characterize those and understand those a little better. Before that, you may have natural philosophy, right? But it's that kind of the last big step in sort of nailing down what we might think of as the ability to really do science happens when we can finally sort of, address the idea that when we make measurements of the physical world, those measurements aren't perfect. They're not exact out to the, 536 decimal place or something like that. And so we need to talk a little bit about that. By the way, a lot of philosophers of science say that's a piece of what's going on there in the middle of the 19th century, along with some other things that lead to the development of a more modern scientific model, but that's not unique. And I probably follow along that framework. There are some other things going on. We've talked about Ewell's contributions and all of that, but all of that comes together at about the same time to form what we think of as sort of modern science. So let's talk a little bit about two things. Let's talk about error and let's talk about uncertainty, because those are two different things, and a lot of folks who think about science don't recognize that those are different. So error is it's a mistake. And now error, when I talk with my students in my science classes, I sort of talk about it in a couple of different ways. Errors always originate in some way, shape, or form with the scientist, right? Errors can be, one of the things that I sometimes talk about with my students, and they can be systematic errors. So let's say you have an instrument and you miscalibrate the instrument, or the instrument has a problem with it that causes every measurement that it makes to be shifted off by a certain amount. The example I use with my students is, let's say you take a meter stick, and that meter stick's a wooden meter stick and it doesn't have metal end caps on it, and so over 20 years of use, what'll happen is you see old meter sticks, you can see this pretty clearly, is the ends of the meter stick, as it gets banged around and dropped on the floor and run into things, sort of wear away a little bit. And you can lose a millimeter or two off the length of your meter stick. Now, if you use that meter stick to make measurements, well, that can throw in an error into your measurements of a millimeter or two every single time. Another example, one that might be relevant in our case, might be, using a telescope, and you want to make brightness measurements with a telescope. Well, one of the things that you've got to do is you've got to sit down and you've got to sort of get a comparison field where you're kind of looking at something that you think is pretty dark. And then you have a star that you say, okay, this star is a star. I know absolutely what the brightness of that star is. And so you look at the dark spot, and then you look at the star that you think the brightness to, and you look at the dark spot, and then you go and you look at the thing you want to measure the brightness of, and you go back and forth and you do that. Now, there are a couple of things that can happen in there. One, maybe the spot that you pick that's dark isn't as dark as you think. Or maybe, your reference star that you think the brightness of, you don't actually know the brightness of as well as you think you do, or the brightness of that thing changes. Great example of that is Polaris, right? Polaris was used as a reference star for a number of years until somebody started to sort of figure out, wait a minute, our measurements seem a little hinky here, and they realized that Polaris is actually a slightly variable star. And all of a sudden, all of those measurements that used Polaris as its reference star, now you knew you had some sort of ongoing systematic error, right? But the other thing that might happen in terms of user error is the user doesn't follow that kind of a procedure. Maybe the user says, hey, I know my telescope's fine, it's great, and then says, so I don't have to do this calibration every time. I'll calibrate it at the beginning of the night, and then I'll be fine for the rest of the night, not realizing that as the atmosphere changes, or as the patch of the sky you're looking at gets higher or lower, and so the starlight has to come through more or less of the atmosphere, it gets bent by more or less of the atmosphere, or different ways. All of those things contribute error. Those things, errors, can always be eliminated. What's different is, or the other thing that you've got is you've got what we call uncertainty. And uncertainty is not something that can be eliminated. So there are about two or three different ways of thinking about uncertainty. And the first thing I always talk about with uncertainty is what's called instrument uncertainty. Your instrument, whatever it is that you're using, has an inherent, built into the instrument, uncertainty. Great way to think about this, there's kind of two ways. One is to think of a stopwatch, right? So, maybe you get the stopwatch on your cell phone, or maybe you've got an old style stopwatch, whatever. But if you've got a digital stopwatch, let's say that digital stopwatch reads out to hundredths of a second. Well, that's great. And you go out there and you measure, you time some event, maybe it's a runner running down the track or whatever. And when you hit that button, the thing that's interesting is that instrument is either going to show you, maybe it's 4.86 seconds or 4.87 seconds. It can't show you anything in between those two values. It can't do that. And so what you know there is if your runner, let's say it's a runner, is 8.64 instead of 8.65, but let's say it's 8.644, you don't get that thousandths of a second piece. That's not the instrument can't tell you that. That's what we think of as instrument uncertainty, especially in digital measuring. In analog measuring, so you put using a meter stick, sometimes you can estimate in between divisions, but still that's an estimate and there's an uncertainty in that. All instruments have what we call instrumental uncertainty. And one of the things you have to do as a scientist is you have to recognize this is my instrument's uncertainty. Plain and simple. Generally, when taking measurements, you're not going to do any better than the instrument's uncertainty level. Normally, when we talk about instrument uncertainty, by the way, we're talking about a theoretical value. Okay, we're not talking necessarily about an actual value. We'll talk about that in a minute. So that's like I say, that's that stopwatch, the theoretical instrument uncertainty is at 0.01 seconds, your meter stick or whatever. By the way, to lower the amount of instrument uncertainty always costs you more money. That's why sometimes when you start hearing about these big scientific instruments and you go, oh my gosh, why are they so expensive? That doesn't seem like a very difficult experiment to do. Usually it's because you're trying to get instruments that measure very, very, very accurately. Now the second type, or the sort of the second source of uncertainty, is what I call environmental uncertainty. When you're talking about environmental uncertainty, these are factors outside of the instrument, outside of the experimentor's or the observer's control in the environment that can change, basically how well your measurement protocol is going to capture what's going on in the physical universe. So one of the things, again, I talk about this in one of my introductory classes. If I've got a meter stick and I'm measuring something, that meter stick might have say an instrumental uncertainty of 1 millimeter. And if I'm measuring something in the classroom on a nice, steady, solid table, I can probably assume that instrument uncertainty is a pretty good estimation of what's, the uncertainty in my measurement. But now let's just take that exact same experiment. I take the table, I put it back in the back of a pickup truck, and then I take that pickup truck and I drive it down a rutted country road. Now, the instrument may be able to measure down to to 1 millimeter. But now when I'm trying to use that instrument to make a measurement in the back of that pickup truck and it's bouncing all over the place, that's going to be a much harder measurement to take. Whatever I'm trying to measurement's rattling around, my instrument's rattling around, and I may decide that, the best I've got here is about a 5 centimeter uncertainty based on environmental factors. When we're doing real measurements, it's hard sometimes to determine what those environmental factors are going to be, or oftentimes it's hard to determine how to eliminate them, if we can eliminate them at all, right? In the case of our making our measurement in the back of the truck, well, okay, maybe, we stop the truck to make our measurement and things gets better. But if we're trying to make measurements on, say, a spacecraft that's lifting off and it's rattling around as it takes off and all of that stuff, maybe that's not something that you can do, right? In the case of telescopic uncertainty, right, one of the things we're trying to do is we're trying to look through an atmosphere that's not stable. And so we may get a theoretical instrument uncertainty on some big telescope that's down in the thousandths or tens of thousandths of arc seconds. But then that telescope has to look through the atmosphere. Well, it turns out that usually the best seeing on the planet through good, stable atmosphere turns out to be about half an arc second. If that's all you've got going on, your environmental uncertainty is never going to be better than that. Now, there are a whole bunch of things that we do with making astronomical observations. Things like we observe in multiple different wavelengths, especially wavelengths where you don't get the atmosphere, like in radio, for example. The atmosphere doesn't necessarily cause as much problems. Or we use things like adaptive optics systems and all of the work that goes into that. But there's always some kind of set of environmental uncertainties. Now, what's interesting about these environmental uncertainties is when you actually do an analysis of them, it turns out that most of the time, not always, but most of the time, those environmental uncertainties are fairly random in nature. Sometimes the environmental uncertainty skews your observation one way, but it's just as likely to skew it the other way. Great way to think about this is, rolling a die. If I get out there with a typical six-sided dice and I roll that six-sided dice, let's say I have some theoretical value that I'm supposed to be measuring for, say, the brightness of Betelgeuse, right? And then if I roll a 1, well, that means the environmental uncertainty shift, right, the observation, say, to brighter. And if I roll a 6, it shifts it to dimmer. And if I roll it to 2, it's brighter, but not as much as 1, et cetera, et cetera. Well, it turns out you can characterize that randomness by the use of statistics. In fact, one of the things that's really interesting, Alter talks about this in some detail in his book. When the original work was being done to define the length of a meter and the uncertainties, both instrumental and environmental, that cropped up that the original guys didn't know how to take into account, that data set was used later on as a way of sort of determining some of the things needed to develop that mathematical discipline of statistics and some of the tools that are in there. So some of the things that you'll see used are things like you can take averages of data sets and then standard deviations of data sets, or standard deviations of the mean. A number of other tools come out of statistics that allow you to characterize, you can't eliminate, but you can characterize the size of that uncertainty, and that turns out to be really important. Of course, as we're talking about Betelgeuse here, there are a lot of factors that go into making that uncertainty a little bit bigger than we would like. Right? One of the ways that you can get rid of that is you make, or at least sort of characterize it, not get rid of it, but you can make it smaller or characterize how big it is take measurements using a lot of different methodologies, right? So you can use ground-based telescopes using visible wavelengths, ground-based telescopes using radio wavelengths, you use space-based telescopes, you can just use all of these different sorts of tools, and you hope that what happens is you're taking those data, what happens is your data begins to converge towards a well-accepted number. And that seems to be going on with a lot of these numbers for Betelgeuse, but there's still some wiggle room in this. So that's, sort of a conversation about when you're doing science, you just sort of have to recognize, and this was really hard, by the way, back in the 19th century for these savants. They weren't called scientists quite yet, and they weren't called natural philosophers anymore, so they were somewhere in between, so oftentimes you'll hear them called savants. That was a really hard thing for them to get their head around, that science wasn't going to give them perfect data, right? And by the, like I say, by the middle of the 19th century, there sort of is this understanding that, no, the natural world, while there may actually be a number, you can't get at it because there's stuff between you and that number. There's random uncertainty, there's instrument uncertainty, there can be user error, those sorts of things. And so as science has developed, that's one of the things that's really become a super important thing to work at. So let's get back to talking a little bit about Betelgeuse. Betelgeuse, as we said, is a variable star. Okay, that means, like we said, its brightness gets brighter and dimmer. We can observe that pretty directly. Right? We just, you get out with a telescope and a photometer, and over time, you just observe the star and its brightness. And what you find out is it gets brighter and dimmer. Okay. And that's a big part of what of course makes some of the thing that's difficult is it turns out that when we talk about variable stars, some variable stars, that oscillation, that change in brightness, that bright, dim cycle is really super regular. One of, two of the types that we've talked about in the past are Cepheid variables and RR Lyra variables. Both of those types of variable stars, their period of oscillation is really straightforward and really simple. It's nice, uniform, it gets brighter and dimmer on a 3.6 day, period or whatever. Betelgeuse isn't that kind of star. Okay, it turns out that Betelgeuse seems to have some things going on, and there are multiple cycles that interact. So let's talk a little bit about that. First off, we don't know what causes all of the variability. We have some models that we'll talk about here in a minute, but it seems that probably the best predictive model that we've got is something that sort of predicts that there are 3 different cycles, each with sort of different amounts of time it takes from the cycle to go from bright to dim to bright again. One of these cycles seems to be related to the other way in which Betelgeuse is variable, and that is Betelgeuse, as we sort of mentioned, we have some measurements by looking at the disk that Betelgeuse is changing size. It's getting bigger and smaller. And by the way, that's something that's predicted by our models, so discovering that wasn't surprising necessarily. But the thing that's kind of interesting about that is that's only one of the things that we think affects its brightness. There are other things that we know are affecting its brightness that we don't know exactly what's going on there. Okay, there are some models, there's active scientific research going on into that, but we don't. It's not something we just have completely nailed down. So the thing that's going to happen here is that these 3 cycles, if you just had one of those cycles, right? Let's say a longer period cycle that was, say, 21 days or something, right? If you have a longer cycle, that means the star gets bright, and then about 11 and a half days later, it's dim, and then, 21 days after that, it's bright again. And that'd be kind of like what you'd see with some of these really regular period variable stars like Cepheid variables. But when you get multiple cycles, what that means is sometimes the peaks overlap, and when the peaks overlap, the star gets really bright, and then sometimes you get the peaks of the various cycles fall at the kind of come at times when other cycles are in dips or troughs, is what you'll hear it called, but low periods of low brightness, and the star's brightness doesn't change a whole lot. And then sometimes you get it to where all of the sort of the low points line up and you get a really dim cycle. That's what we really right now, by the way, think's going on with Betelgeuse. What we think here is that as these 3 cycles interact, sometimes you're going to get a point where they all line up and you get these really bright points where Betelgeuse is going to be really bright. Remember, that's one of the things that John Herschel observed. And, at a couple of points about 10, 15 years apart, he saw this time when Betelgeuse was brighter than Rigel. What that means is you're also going to have some times when Betelgeuse is going to be really, really dim. And if you sort of sit down and you do the math, it turns out that what we see here is this is a period of time when those 3 cycles should probably interact to produce a fairly dim Betelgeuse. As dim as we're seeing now, that's harder to say, and here's why. Because we don't understand in some cases the causes for these cycles, we also don't understand how the cycles interact with each other in a physical sense. So it may be the case that what goes on is every once in a while when these cycles start to line up, there are some physical interactions in what's going on inside the star that cause it to be even a little bit dimmer, or when they line up and they're all bright, to cause it to be even a little bit brighter. And so those interactions may sort of amplify the effect of the cycles lining up, and that's sort of the explanation that you're getting from a lot of astronomers right now. So let's talk a little bit about what's going on physically in Betelgeuse to kind of get a sense of what's happening. And in this case, this is one of those things that we didn't talk a lot about in our Finding Our Place in the Universe episode or series, because this wasn't really the point of that series. That was about sort of, like I say, it was about cosmology. We weren't talking about, say, stellar life cycles and that sort of thing. We touched on it a little bit on those series of episodes when we were doing stellar spectroscopy and, the work of Eddington and all of those guys, but let's see if we can sort of bring this together a little bit. The big tool, by the way, for this is a diagram that we talked about back in that series. It's sometimes called the Hertzsprung-Russell diagram, or just the HR diagrams, which you'll hear it called a lot more often now. And the HR diagram is really a diagram that sort of, in a sense, talks about on one axis, it's a graph. And on one axis, you plot how bright the star is, and on the other axis, you plot the color of the star, or, more indirectly, you plot the temperature of the star. And so every star has a spot on the HR diagram. Well, the thing that's really strange about that is the plotting of a star on the HR diagram all by itself doesn't tell you a lot. What you'd really like to know is sort of, does the star move around where it's at on the HR diagram, or does it stay in a place? And that allows you to determine sort of a life cycle for the star. Now, this can be a little esoteric, so let me use an example maybe that's a little more accessible. let's say you want to have, instead of, what we call the HR diagram, which, like I say, might be a brightness temperature diagram, luminosity temperature diagram, something like that. Let's say we want to look at human beings and we wanted to create sort of an age height diagram. Maybe on the vertical axis of your graph, you're going to put somebody's age. Horizontal axis of the graph, you're going to put their height, or maybe the other way around. I don't know. It doesn't really matter. And what you did is that over time, you could sit down with a single person and you could watch them for the entire time of their life. And of course, what you would find out is that when they're very young, they're also not going to be very tall, right? They might be pretty short. And then, what you'll do is if you think of that as a point on the graph of what those two numbers are, that point's going to move on the graph as they start to grow up. As they get older, they're going to get taller and they're going to move up on the graph. But then at some point, what's going to happen is age-wise, they're just going to sit at the same point they're going to sit at the same height on the graph, right? And then maybe, as they get a little older, what they'll do is, because of things like osteoporosis and cartilage shrinkage and all of that, you begin to find that you lose a little bit of height towards the end of your life. Well, the thing that's kind of interesting is that then by sort of looking at what their height's going to be, you get a kind of sense, you can correlate their height and their age a little bit. Now, let's say, though, you don't have 100 years to watch a single person, right? That gets tricky, right? Now you can't necessarily do that very well. So the idea is instead what you might do is you might say, okay, what we're going to do is we're going to go sample a whole bunch of people, and we're going to sample them at different stages in their lives. So maybe you go to a town, right? You go to a town of maybe, 50,000 people, and you go into that town and you sit down and you're able to do surveys and how old are you, sir or ma'am, and how tall are you, and you could maybe sit down and start looking at putting together sort of a diagram of where all the people are in terms of their age and their height. And what you may find is that you'll get this sort of a band where you get the sort of everyone sort of sits along this band through most of their lifespan. But what you'll find is that early in their life, they'll all have this thing. You'll see, because you'll have these people between ages 0 and maybe, 18 or 20, right? Their heights are still getting taller while their age. You may see growth spurts in there. You may see all of that. And you may be able to determine sort of a relationship between their height and their age. We can do a similar kind of thing with stars, right? Except that instead of we can't go to a town of stars, well, except that we kind of can. We can go to clusters of stars. And by looking at the clusters, sometimes the clusters we can see hundreds of members, sometimes we can see thousands, sometimes we can see tens of thousands of stars in these clusters, and we can do a similar kind of thing. And when we do that, we begin to recognize that on the HR diagram, there's sort of this band where most of the stars are. And it's called the main sequence. And most of the stars sit on that band, and, they're kind of just hanging out there. We see places where, you can sort of see stars in early stages of formation. They're moving across the HR diagram. This would be kind of like, human beings growing up. But then the thing that's really interesting is what we see is that in the HR diagram, we begin to see that above a certain point, we see this really big change, right? And we call this, by the way, a turn-off point. And what we do is we begin to see that the thing that's really interesting is that the stars' luminosities really get bigger. They get bigger a lot. And oftentimes what we see is that their temperature gets cooler. And so the thing that's interesting is when we look at different clusters, we can look at those clusters and we can put, we can put all the stars on an HR diagram. And one of the things that we find, of course, is that when we look at those clusters, the younger the cluster is, the fewer stars there are in that part of the HR diagram after the turnoff point. In other words, the younger the cluster, the fewer stars have undergone whatever that change is after that turnoff point. Okay, so now put a pin in that. We're going to come back. At the same time we're sort of doing that research and we're starting to get really good sense of that, you have a thing happening on the theoretical side. And that theoretical side, and we talked a little bit about this when we talked about the work of Arthur Eddington, right? And Eddington and Mills and Jeans, they were all working on models trying to figure out what allowed stars to produce light. And the early versions of those models were all models where it was thought that the light that was being produced was a light that was being converted from heat energy into visible light. Now, in all of the early models of this, the key physical principle, and by the way, this is going to be the key physical principle throughout this, is something called hydrostatic equilibrium, is the big fancy term. But it's really, it's an easier thing to sort of understand than the term makes it sound. And that is, as you have energy in the interior of our star, however that energy is being produced. In the early models, it's just the fact that what you've got is you've got all of these gases and they're getting squeezed together, and so they heat up and they bounce around. All of that energy wants to push the star outward. But balancing that is you have the fact that all of the mass of that stuff creates this gravitational pull that wants to pull all of the material towards the center of the star. And so all the early models, starting back all the way back with Kelvin's early models and Helmholtz's early models, up through these models of Eddington, Milne, Jeans, and those guys, all use this hydrostatic equilibrium. And what happens is, the star wants to collapse because of gravity. This internal pressure holds the star up. As some of the heat energy of that internal pressure gets converted into light, the light leaves the star, and the star will slowly collapse over time. But the problem is that in those models, those earlier models, the star just didn't live long enough, right? The star would last maybe, 10 million years, but we had evidence on of the Earth being billions of years old. Well, all of that changes in 1925 when Eddington says, hey, if I take Einstein's ideas in relativity and the equivalence of mass and energy, and I say that there's a process in the core of this star that allows hydrogen atoms to be fused into helium atoms, there's going to be a little loss of mass there. And that mass is going to be converted into energy, and maybe that's the energy source that tries to push the star outward. Okay? And that's really a cool idea, and everyone just sort of is blown away by Eddington's idea. In some ways, that's his last great, truly generationally altering idea. And it turns out that in time, and the problem is, of course, then you can have some difficulties. You can have a world war and a huge depression in the middle of that. But after the war, guys like Hans Bethe are going to sit down and they're going to work out the math for that. And what they're going to come up with is the fact that does, in fact, is what sort of creates the hydrostatic equilibrium. And as long as you're fusing hydrogen into helium, you can produce a steady source of energy to balance that inward gravitational pull. And that's going to be really super stable, and it's going to last for a long time in terms of the total life of a star. And so they figure out that that's why stars are mostly sitting on the main sequence. For our sun, based on its mass and all of those kinds of things, that's about a 9 billion year time frame that our sun is in its core going to fuse hydrogen into helium. The energy that is released from that fusion by the conversion of just a little bit of mass into energy is enough to balance or hold up the gravitational contraction, and the sun stays relatively stable during that period. And we're about halfway through that 9 billion year time frame, right? And then our models now have that there are some changes and all of that, but things tend to remain remarkably stable in there, at least until you start to run out of hydrogen in the core. Sooner or later, you start running out of hydrogen to fuse into helium. And then, and this is, my graduate school advisor, Dr. James Hunter, used to always say, gravity, the pathological beast, always wins. As you start to run out of that hydrogen fuel, now you can't produce enough energy to balance the gravitational inward pull. And so what happens is the process of collapse that formed the star so how many ever millions or billions of years earlier recommences, and the star begins to collapse again. And as the star begins to collapse again, temperatures at the core of the star get even higher. And one of two things happens. Either what happens is you begin to get things hot enough that you get a shell on the outside of the core begins to fuse hydrogen into helium, or the core itself gets hot enough that it begins to fuse helium into heavier elements in a process we call the CNO cycle, but you produce carbon, nitrogen, and oxygen in that. Okay. Now, that process, once you get into, sometimes it's called shell burning or shell fusing, or you begin to hydrogen or helium fuse, that's not nearly as stable as hydrogen fusion. And so a couple of things happen. First off, once you get shell burning, even as your core continues to collapse, that shell burning is going to push the outer envelope of the star to a much larger size. And that's going to push the star into what we call a giant phase. Also, the thing that's going to happen is as that takes place, as that envelope increases, it's going to cool down, which means the star is going to go from whatever temperature it was to becoming much redder. And so what you get are you would call these red giant stars. Now, if the star has a lot of mass, it turns out that that process can go on in a number of different ways. And I'm not going to get into all the details here because this is really a discussion of what's going on with Betelgeuse. But that star, one, is going to go through several cycles of that, and it can have several types of shell fusion, right, with the outermost being hydrogen into helium, but then we'll layer inside of that helium into something else, et cetera, et cetera, et cetera, to where then down in the core, you're fusing in the core some pretty heavy stuff towards what we call iron, all right? But what's going to happen is, because this process is not particularly stable, is you're going to get stellar pulsations. And so what we think is going on is when you move into these giant, or if you are a very high mass star, something like Betelgeuse, which is more than, 5 times the mass of our sun, 3 or 5 times the mass of our sun, those are actually known as supergiant stars because they get really big and really bright. Okay. That what happens is that these processes, you get pulsations, okay? And these pulsations are not particularly stable, and it's not really clear, or not really clear, I shouldn't say, but the models describe that, your star is going to get brighter and dimmer, and it's going to oscillate. We think that's what's going on with these Cepheid and RR Lyrae variables. They're actually giant stars undergoing regular pulsation levels. And that's really interesting. The other thing, though, is when you get to these supergiant stars, and that's definitely what Betelgeuse is, what seems to be the case, we have clear indications from imaging the surface. And again, we can image the surface of the star given the what's happening with our observational techniques, is there's some real strong indications that what you have is these huge sort of upwelling of material from deeper in the stars. We call them convection cells because that's the physical process is when you have a hot material and it gets transported. We call that convection, right? And usually, the best way to think of that is when you put a pot of water on the stove, right? And you heat the bottom of the pot. And what you can do is you can sort of watch the water near the bottom of the pot because it gets hot and it gets a little less dense. It rises to the top and the stuff that's cooler at the top sinks to the bottom. That process, we call that convection. And so what we think is that there are these huge convection cells going on in Betelgeuse that are in part, that convection process is driving some of not only the pulsations, but the changes in brightness. Now, down inside of the core of Betelgeuse is you have this thing where you're still fusing heavier elements into even heavier elements. So the thing that's kind of interesting about that, though, is you can't do that forever. And the reason is that when we fuse hydrogen into helium, that gives off a little bit of energy because 4 hydrogen atoms has a little more mass than a helium atom. And so when you lose that little bit of mass, you give off some energy. Well, that works just fine up until you hit iron. And then once you try to fuse iron, turns out to fuse iron into something heavier than iron, that costs you energy. You're no longer producing energy to balance the gravitational contraction or the gravitational pull towards the center. You're now grabbing or consuming energy, and that's going to spell the death of a star once you get to that point. Now, the thing that's really interesting, and we'll talk about that here in just a moment, So the thing that's really sort of interesting is the final piece of all of this is it turns out that when you do the math of how much hydrogen you have to fuse to balance the gravitational inward pull, it turns out that the bigger the star is, not only do you have to fuse more hydrogen, and that makes sense, right? If you're a bigger star and you have more mass, the gravitational pull's bigger, so you have to fuse more hydrogen. But it's not a linear kind of thing. It's not like if you have to, you're double the mass of the star, you have to fuse hydrogen twice as fast. It's actually, it goes as the fourth power. It's a huge, so basically what you have to do is if you're double the mass, you've got to fuse hydrogen 8 times as fast. Which means that even though you have twice as much hydrogen, your lifespan's only going to be a quarter of a star that's, say, 1/2 your mass. So what that basically means is that when you look at that, stars, generally, the bigger you are, the shorter your life is. And it's a pretty dramatic shift. So one of the things that's really interesting is that for a star the mass, we think of Betelgeuse. And that's a star, roughly 10 or 11 times the mass of the sun. A star like that, when you do the model calculations, you get a star that's lifespan isn't 9 or 10 billion years like our sun's. You get a star whose lifespan is in the, roughly 10 million year time frame. In other words, the thing that's really interesting is that star's only going to last 1/1000th of the lifetime of the sun. So what we know is that Betelgeuse started out, it lived on the main sequence, and it's now off the main sequence. It's now no longer fusing hydrogen in its core, it's fusing other stuff in its core. It's now what we would call a red supergiant star. Now, the thing is based on our models, that star has about 100,000 years before in its core it can no longer fuse things together and get energy. Now, if that's the case, if our models are right and we've got about 100,000 years, well, the thing that's interesting is this is where that Chinese observation becomes really interesting. The Chinese observation of Betelgeuse as a yellow star as opposed to being a red star means that in their observations, say in, maybe 500 BCE, Betelgeuse is just really entering this last stage, which means that, we're 2,000 years since then, 2,500 years since then. Betelgeuse has still got 100,000 years before it should reach that endpoint, if those observations are going to be trusted and if our models are correct. So the claim that you'll hear a lot of times is, or you've probably heard in reference to some of what we're talking about here, is that, oh my gosh, Betelgeuse is getting dimmer. Maybe it's about to do what's called going supernova. So what is that? When we talk about a star going supernova, that's when, like I say, it's got so much iron in its core, it wants to try to fuse that iron. The problem is it tries to fuse that iron, it ends up costing energy instead of giving you energy, and then you get this incredibly rapid collapse of the star's core. How rapid? Usually that core will collapse in about, our models show, about a quarter of a second, right? As that core collapses, it gets down to a state where it hits something to where the electrons are forced into the atom, combine with the protons to form neutrons, and you get this sort of very rapid stop. And all of the other stuff that comes down hits that and bounces off in a sense. And you get this huge release of all of this energy and all of this material that gets blown back out. And that release of energy is an enormous amount of energy, because now we're not just talking about the fact that we're fusing, atoms into bigger atoms. Now what we're doing is we're talking about process within the nucleus itself with elementary particles. What you've got is you've got electrons going in, they're getting combined with protons, and you've got stuff going on down on the quark gluon level, and that releases incredible amounts of energy. That's what goes on with a supernova. We've had this happen a couple of times in living memory. In about 1054, we had a star that is now, we call that what's left over, the Crab Nebula, but we had that explosion happen in 1054. Again, during Kepler's lifetime, there was a supernova in the constellation of Cassiopeia, right? We've seen these sorts of things. And as those things have happened, depending on how far away your object is, well, it depends on how bright you're going to see it. So the thing was interesting in the 1054 supernova, it was bright enough. It could be the remnant of that supernova could be seen during the daytime sky, right? For a couple of months, it was brighter than the full moon. It could be seen during the daytime sky. Thing that's really kind of interesting is we've got depictions of this from Native American tribes. We have it from Chinese astronomers. It seems to be less well documented in Europe for reasons that not everyone quite understands. But, we certainly have that. Again, Kepler's supernova, because the star was farther away, it was not as bright, okay? And so it wasn't something you saw during the day, but you definitely would see it at night. So the thing that's interesting here is, before we sort of get to this last piece where, what would that look like if it happened? Let's understand very quickly sort of the takeaway from everything I've just said. First off, is Betelgeuse going to go supernova in the next 2 weeks or something? Most likely it's not. All of our models say it should have another 10,000 years or so. So what that means is probably Betelgeuse is not gone supernova. What we're seeing here is we're just seeing a temporary, really dim period based off physical processes that lead to the variability cycles. Those are combining. They give us a dim star. The star should brighten up here. And like I say, I'm recording this in January of 2020. So it should require, or it should brighten back up here in the next couple of months. And by, June or July of this year, it should be fairly bright. However, it is possible that our models aren't quite right, or we've got the timing off a little bit. And yeah, this would lead to, a supernova. How likely is that? Highly improbable is the best way to think about that. Now, a couple of other just neat things, just a couple of pieces of information here that I think you just might find cool. First off, if Betelgeuse really only has like a 10 million year lifespan, what that really means then is if the KT impact 65 million years ago, when the big meteor hits the Earth near the tip of what's now the Yucatan Peninsula and sort of extincts so much of the planet, Betelgeuse wouldn't have been in the sky, and wouldn't have been in the sky for another 55 million years. So, Betelgeuse is younger than the dinosaurs in a sense, which is really an amazing thing to think about. Secondly, the thing that's kind of interesting is that, given the fact that, supernova are just such dramatic events, if we do have some things wrong, it could be that Betelgeuse has already exploded. And because it's going to take 600 years for the light to get here, it may have exploded 300 years ago. And we still got 300 years to wait. And that's kind of a wild thing to think about as well. So let's kind of get to the last piece, and then we'll wrap up here. And that is, what would a supernova look like here on Earth? As I've sort of indicated, given what we know about Betelgeuse, it's going to do a typical, what we sometimes call a type 2 supernova, is what the models all say should happen now, which means it's going to look an awful lot like what happened in 1054. This thing will explode. It's going to produce an enormous amount of light because of the sort of the way this thing works, and the fact that the star has actually been shedding its outer layers over the course of the last couple thousand years. You're going to have things that are going to interact with those outer layers and light them up, and they're going to be super bright. And so what we're going to see is probably for 3 months, we would be able to see this probably during the daytime, right? It would be something you would go out and, much like if you go out during the day and you can see the moon in the daytime sky, you would see whatever this would look like. And it would, it would look like, sort of a slowly expanding bright patch of light. At night, it would be brighter than the full moon. The accounts from the 1054 supernovas you could easily read by the light of that supernova. That would certainly be the case with Betelgeuse. A second question that a lot of times gets asked is, are we going to have any advanced warning of this going on? Well, depending on whether we're able to sort of improve our observation abilities, we might be able to sort of determine some of the oscillations and do a little better imaging of the surface. But our best chance for advanced warning actually comes through neutrino detectors. So it turns out that in the process of fusion, in addition to producing light, what usually happens, you produce these little these elementary particles known as neutrinos, and we talked about them in our second series. They're really quite interesting, but because they're neutral, in other words, they don't have any electric charge, and they're very, very low mass. They don't interact with regular types of matter very much. You have hundreds of thousands of neutrinos streaming through your body right now that have been produced, by the sun and other stars, and they just stream right through the Earth, and they stream through your body, and it's no big deal. The thing that's kind of interesting, though, is that every once in a while, if you've got sort of the right kind of arrangement of matter in a chemical sense, what'll happen is the neutrino will interact with that piece of matter, and that piece of matter will produce a bit of light. And so what we do is we can actually create these things, these neutrino telescopes, and we got to put them way, way, way underground usually. And they're big vats of cleaning fluid, basically, and surrounded by these light detectors. And so when a neutrino comes in and hits one of these molecules of this cleaning fluid just right, and it causes that cleaning fluid molecule to give off a little bit of light, we can detect that there's this neutrino, right? Well, the thing that's interesting is that because neutrinos don't interact with anything, when a supernova happens, the neutrinos are going to leave that supernova immediately. The light produced by that supernova has to interact with all of the matter between the supernova and us, most notably all of those, all that matter that's sort of been given off by the outer atmosphere of the star, which means it's not going to get here. Once it gets out of that, it's going to travel at the same speed of the neutrinos, but that's going to slow it down for a little bit. So the idea is that what we may see a big spike of neutrino detections, and on these neutrino detectors we have all around the world, and then we would see the supernova, right? We would see the light come from the supernova. How big a warning? I've not seen a lot of good information about that. I don't know if it's on the order of minutes or if it's on the order of hours. It's certainly not on the order of days, at least from what I've been able to see. But there is a chance we would actually see a spike of neutrino detections that would let us know that something's coming. The final thing is what other kinds of effects, other than, just sort of changing what the nighttime sky looks like, and then as the thing fades out, changing the fact that Orion would no longer have that at least from our view, that right-hand shoulder. What effects would this have? I can remember as a young student, there was always a lot of sort of conversation if one of these great big supergiants near us, right, Antares or Betelgeuse or something like that, exploded, what effects would that have? And they were always sort of alarmist kinds of conversations about, the big giant X-ray pulse of the star in the supernova would shred our atmosphere or heat up our atmosphere and kill us all. I mean, there were all of these very, very alarmist kinds of things. What it turns out is that, at 600 light years away, it's not going to do a whole lot. Right? We might see just small influences and effects on a few things, but nothing that's going to be significantly disruptive, nor is it going to do anything to anything on the surface of the planet. So with that thing, if you in looking at some of the less credible media sources, you get somebody who sits down and says, this is going to be a disastrous thing and wipe out half the people on the planet or something like that. And I'm sure, in some point in time, you can probably go out on a YouTube channel somewhere, and there's going to be some, snake oil salesman that's going to want you to donate all your money because we're all about to die in this supernova, and he can promise you passage out of here somehow. The kind of the story. None of that's going to be true, right? What this is going to be is very much like the 1054 supernova, if it in fact happens. And like I say, we may be waiting another 100,000 years for that. Probably we're waiting another 100,000 years for that. So I hope you've enjoyed this sort of brief exploration of some of these sorts of things. I've tried to keep things somewhat non-technical. I don't know how well I've succeeded. I may be in doing that. I've actually made this worse. There are a number of great astronomy-focused podcasts and YouTube channels out there that have done a nice job talking about this. The one I would probably recommend is the Astronomy Cast. It's been around for a long time. Pamela Gay, Fraser Kane, they both have YouTube channels as well, and they do great astronomy conversations and discussions. And so that would be a good place to go out and see if you can find some information about this if you want to. Phil Platt's Bad Astronomy website is also very good on this, and he talks a little bit about this in some more detail in his blog and in some of his writings. This is another resource that you might want to use. So our next episode, we'll get back into the conversation about geography. So until then, full sails on your journey.